Welcome back, everybody. Episode 79. Episode 79. I think. I always forget. I don't know why. Yeah, episode 79. We got a slowpoke today. I'm going to check out. Oh, whoops, my microphone. My bad. Alright. Let me fix that microphone. What's going on here? Okay. I think we're good. Check out our slowpoke sound. Let's check out this one.
I have 10 years of experience.
This job requires a college degree. Any degree.
How's that fast floating the sky? What a sound, bro. Slow. How's that sound? Oh. Slow. There we go, bro. Okay. So we're going to continue today with our Leetcode patterns. I think we got another grid problem. Yep. I'm going to avoid that for now. Okay. I'm going to take a look at some greedy algorithms today. 2 out of 50, geez. A lot of greedy problems. Gas station. Kind of want to learn a little bit about maybe some greedy algorithms. Ooh. Okay. Check out the binary tree tilt. Ooh. Oh. Given the root of a binary tree, return the sum of every tree node's tilt. The tilt of a tree node is the absolute difference between the sum of all the left subtree nodes and all the right tree subtree node values. If a node does not have a left child, then the sum of the left subtree node values is treated as 0. The rule is similar if the node does not have a right child. So we have 1 here. Tilt of node 2. 0, 0, no children. Tilt of node 3, 0, 0, no children. Tilt of node 1. 2 minus 3 is equal to 1. Left tree. 0 plus 0 plus 1 is equal to 1. Okay. Tilt of node 3, 0. Tilt of node 5, 0. Tilt of node 7, 0. Tilt of node 2. 3 minus 5. And we have tilt of 9, which is 0 minus 7, which is 7. Tilt of node 4 is 2. 2 minus 9. Tilt of node 4 is 3 plus 5 plus 2. Okay. How's hmm. I was thinking my intuition was more like BFS here, but like obviously not starting from the top, but somehow maybe starting at the bottom and traversing by level. Like a reverse BFS traversal. I don't know if that's a thing, maybe not, but doesn't really seem like it. Now I'm starting to think this is probably more DFS. Flows left, right, root. So maybe we somehow go all the way down. We see a child node. We return 0 for the child node. Go back here, add these two values. And we kind of go back up the tree. Then go down the right subtree. I think that's my idea here. Passing our node. I think we probably want the... We are on Steel Series 83.00. So I'm thinking, yeah, we go 0, right? Do 0, 0. There's 0 here, right? 0, 0, which is 0 here. Then 3 is 3 plus 3. I think it's 3 minus 3. 0 here. Then zero, 0. Then we have 1 here. 0, 1. Kind of like the rules a little bit. 0, 0. So maybe we'd have to somehow keep track of... I don't understand how you get this test case here, though. That's the thing. Right? I know we get 0, 0 here because of the child's. Right? The 3 minus 3 is 0, so 0 goes here. Then I thought it was like 0 minus 1 here. Should be 1. I thought. I'm gonna take a look at this. Ask GPT to run me this test case. 63 binary tree tilt. Don't show code. Can you just show me this test case? explanation of this test case. Each of us bottom up. Okay, I'm just gonna follow this test example. Okay, well, if not node, right, we return 0. Okay, that's obvious. If we see a null node, we consider it a 0, right? I think we need to do DFS node dot left, node dot right equal to DFS node dot right. Trying to think about how the recursion would work here, right? So we loop through here. I think we'd have to go after recursion because we're going to need to get back the values of node dot left and node dot right. So it'd be node dot left. Node dot right. What do we return? What do we return in this case? Do we return anything? DFS root. Return 0. We got to return something. Just think about this. What's this code gonna do? It's gonna go past in the root. Instantly call no dot left. No, it's gonna go through. No, it's not. No, it's instantly gonna call no dot left again. Right, and then it's no. There's gonna instantly call no dot left. Right, then it's gonna, if not no, it's gonna return 0. It's gonna return 0 here. Then it's gonna call no dot right. Okay, it's gonna return 0. Okay, come back here. This is what's gonna return 0. Let me check. Well, if node dot val is equal to node dot left plus node dot right. So 0 plus 0 is 0, right? 0 plus 0 is 0. No. A little stuck here. Base case, we return 0. Okay. Compute the total tilt. Tilt is equal to left sum plus right sum. Total tilt, sorry. Self dot total tilt. You got a left sum plus right sum. Then we want to return no dot val plus left underscore plus left sum plus right sum. I'm gonna return self total tilt. Call our DFS function here with our root node. How do we get 5 here? It's because we're adding down here, I think. Because we would return 0 minus 0. I return no dot val plus the left side of the right side. So return 2 here, right? No dot left. Would return 2. Or right, do the same thing. 0, 0, return 3. And then do 2 plus 3 here, which would be 5. But really, I think this should be minus. Oh, but we need the absolute value. There we go. Nice. We were close. I mean, we had the right idea. Just didn't really execute it properly. Okay. The night is still young. Ba, 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 ba. Night is still young. Ba, 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 ba. Wow, look at all this stuff, bro. No, get rid of Google Lens, man. Do not return anything. Modify the root in place. From the root of a binary tree, flatten the tree into a linked list. The linked list should use the same tree node class where right child pointer points to the next node in the list and the left child pointer always is null. Okay. The linked list should be in the same order as a pre-order traversal of the tree. Root left, right. Do not return anything. Modify the root in place. Okay, that's the hard part. We gotta modify the root in place. Can you flatten the tree in place with one extra space? Do not return anything. Modify the root in place. So do we have to use? Okay, I'm gonna make it with an extra tree node, right? So we do fuck, how do we make a new tree node again, man? We make a new tree node. Let's do like root. Should we do? Let's do cur is equal to tree node root, right? do DFS when we're passing our route. If not node, think about the solution. We start from here, we go left. To the left is 2. Oh, I'm trying to think yet. I don't think about how to recursively do this. Like, let's do like a dummy value, right? To return, we do occur is equal to dummy. Oh no, we return, right? Tree node. Software categorize. Software code right. Node left. GFS node right. We just want to return our Back to OG list. Once we do root dot left. You go to none. Then we do root dot right. Dot right. Dot right because I think we do dot right because we skip. We have our dummy here, right? Our dummy points to a -1 node, so we need to root dot right there. But then I think also root is the root node, so we need to return the dot right, which would be the second value, I think. Turn type tree node. Okay. This needs to be no dot val. We got 1-1. Bro, I don't know what I'm fucking returning here. Wrong. the fuck? Love that guy. DFS node. Bro. Call the DFS function here. Oh my god, dude. Call the DFS function here, alright? Start here. Do was get a tree node val, right? Moves right. Then calls DFS left. Okay, we're gonna. Oh, paint looks a little different, bro. Okay, right, we're gonna just draw it here, okay, because, okay, we start with our -1. We go right. Soft dot curl dot right. We pen down node, right. -1. Then we put in our root, right? 1. And then we go node dot left. Node dot left is 2. Right, so it's not null, so it appends 2. Okay. Goes to 3. Appends 3. Calls node dot left again. Returns none. Comes back to 3. Goes node dot right. Returns none. Comes back to 3. 3 doesn't return anything, so we've gone through it. So it goes back to 2. Gets to 2. Calls the node dot right, which is 4. We put in the 4 here. Right? Comes back, returns nothing, goes to the 2. Right? We return both. Comes back to the 1, then goes right, returns 5. Okay. Goes to 6. Okay. Goes to 6 here. Then goes to none, sees none, sees none, and returns. Sees none, returns. We go left first. But it's whatever. Anyway, return none, we go right, we go left. Return nothing, go right, return nothing, return, go back to 1. Return. There we go outside this loop. We check, well, root dot left is equal to none. So our original root, right? We do root dot left of 1. Root dot left is equal to none. Because that is in the question of trap point is always null, right? Return none. Then we make our root dot right, our right value in this tree, equal to dummy dot right, which is 2 here. Then it starts from 2, goes to 3, 4, 5, 6. And that's what it returns. Man. Okay. The night is still young. The night is still young. Okay. Binary tree level auto traversal 2. Let's take a look at this. Level auto traversal. Given the root of binary tree, return the bottom level auto traversal of its no values, i.e. from left to right level, from leaf to root. Oh, okay. A list inside of a list. Okay. I understand. I think this should be pretty straightforward. Import DQ. And so we create a DQ. Sorry, our Q is equal to DQ. Put in our root first. Right. We do while Q. We loop. We do our length is equal to the length of Q. We do for I in range length. Length. We want to pop, so we do well. Node is equal to Q dot pop left. We pop left. And we make like a cur, right? Cur is equal to this. We do cur dot append, no dot val. Right. Let me do well if no dot left. Q dot append, no dot left. If no dot right, we can Q dot append dot right. Then we can outside the for, we want to do res dot append cur, and then we want to go on to our next right, and then we just want to return our res. Okay, let's see what that returns. No attribute value. Alright, let's just return empty string. Okay, right. Return reversed res. Res dot reverse. Can we do res dot reverse? And outside the while, we can do res dot reverse. Then return our res. What is the better one? I guess that reverses too. I mean, it's pretty much the same. Okay. Nice. Level order traversal 2. Let's go. Alright, let's do something different, man. Like, kind of done with tree problems, dude. Jeez. We're getting there though, dude. We're at 52. Ooh. Take a look at some greedy problems. Perfect calculator, reorganize string. Carpooling. Let's do carpooling. I'm curious. So it's like, I know like with a greedy algorithm that like in the future, you don't have to worry about the future because it's like the same. From memory, it's something like that. I don't know. It's like you know what it's gonna be or something. I don't know. Okay. Without considering the future consequences, the goal is to find a globally optimal solution by making locally optimal choices. Let's take a look at some videos, bro. Got the money sign, dude, on this one. Oh, it's on the headset.
Hello everybody and welcome to another YouTube video. So in today's video, I'm going to be explaining greedy algorithms. Now this is really meant to just be an introduction to this topic, so in this video I will explain to you what a greedy algorithm is, how you can go about creating a greedy algorithm, and then show you a few examples of it. But with that said, if you want to learn more and practice with greedy algorithms, what you can do is check out the sponsor of this video. Before we get started, I need to thank the sponsor of this video, which is AlgoExpert. AlgoExpert is the best platform to use for preparing for your software engineering coding interviews and has the highest quality coding interview practice questions. With 160 practice questions, detailed solutions in 9 of the most popular programming languages, a feature-packed browser-based coding environment, extensive test suites, and conceptual overviews and code walkthroughs for each and every problem, AlgoExpert is the best resource to use to ace your coding interviews. AlgoExpert also has a data structures crash course, coding interview assessments, and a mock interviews feature. I can highly recommend AlgoExpert as a former customer myself and now an official instructor on the platform. Get started using AlgoExpert today by clicking the link in the description and using the code TechWithTim for a discount on the platform. So I'm here on my drawing tablet and I'm going to start explaining to you what greedy algorithms are. Now before I do that, I will note that I do have very messy handwriting, so please excuse me. I'll try my best to make everything as neat as possible in this video. But with that said, what is a greedy algorithm? Well, a greedy algorithm is really an algorithm that makes a greedy choice. You can think of this as kind of an optimal choice at every single step in the solution or in the problem. Now, the greedy choice is defined by some rule. That rule could be select the largest number, select the smallest number, select the element that has a certain property. Whatever, you're making some definitive choice, some greedy choice at every step in the algorithm. Now, greedy algorithms can be very complicated. They can also be quite simple. To give you an explanation or kind of an example of a greedy algorithm, let me kind of introduce a problem to you right here. So let's say for this problem, we're given some array, and this array is filled with integers. So I have 3, 4, -1, 2, -3, and 0. And then maybe we're given some integer n. We can say here that n is equal to 4. Now what this problem is asking us to do is to find the n numbers in this array that equal the largest sum. Now if that's the case, the greedy algorithm approach to solving this problem is to simply select the largest number at every single step until we've selected n numbers. And this should hopefully solve the problem for us. So if we apply the greedy algorithm approach, we're selecting the largest number at every step until we've hit 4 numbers. So what we do is we start by selecting 4 because this is the current largest number. So we select 4. Then we select 3 because 4 was already selected. So now we have 3 and 4. Then we select 2. And then finally we select 0. And what we get is 4, 3, 2, and 1, which means that we have an answer of 10. So that's the largest sum that we can create by selecting 4 numbers, and this would actually be our answer here. We would return 4, 3, 2, and 1. So that's an example of a very, very simple greedy algorithm where all we did was select the largest number at each step, and well, that led us to the solution. So I know the example I just showed you is relatively trivial, but it's the best way that I can show you what a greedy algorithm is without getting into any super formal explanations. So as you saw there, a greedy algorithm is really just an algorithm that makes an optimal or greedy choice at every single step, and eventually all of those choices lead to an optimal solution at the end of the program. Now, before I get into some more advanced examples here, I'm going to give you two kind of formal definitions or formal properties of when you can actually use a greedy algorithm to solve a problem. So if the following two properties that I'm going to state are true, you can use a greedy algorithm and you'll be able to solve the problem. So the first property is called the greedy choice property. And what this says is that a global, optimal solution can be reached by choosing the optimal choice at each step. And then the second property that needs to be true as well is the optimal substructure property, which says a problem has an optimal substructure.
Let's write these down, bro. Oh, shit. Oh, jeez. Okay. Type over here. So, like, oh. Two greedy properties. Greedy properties are a global overall optimal solution can be reached by choosing the optimal choice at each step. A problem has an optimal substructure if an optimal solution to the entire problem contains the optimal solutions to the sub-problems. Global overall can be reached by choosing the optimal step. A problem has an optimal substructure if an optimal solution.
If an optimal solution to the entire problem contains the optimal solutions to the sub-problems. So to kind of break that down a little bit, what that means is every time you make a choice, you can kind of treat that as a sub-problem. Now, an optimal substructure exists if all of those sub-problems allow you to solve the larger problem as a whole. So really it's saying if all of the solutions to these sub-problems combined allow you to have a full optimal solution to the entire problem, then you're good. You can go ahead and use a greedy algorithm. So I'll leave those definitions on the screen so that you can read them. I'll give you one more kind of formal definition here before we get into another example. This says greedy algorithms work on problems for which it is true that at every step there is a choice that is optimal for the problem up to that step, and after the last step the algorithm produces the optimal solution of the complete problem. So that makes it seem a little bit more confusing than it really is. What I'm going to do now is move on to another example and show you how we apply a greedy algorithm to it. So in front of me I have a very famous problem which is known as the knapsack problem. Now what I'm going to do is introduce a variation of this problem to you and then explain how a greedy algorithm can be used to solve this. Then I'm going to go back to kind of the original problem and show you how the greedy algorithm fails. So let me introduce what this problem is. So in this problem you have a backpack that has a specific capacity. In this case the capacity is 25. Now that denotes kind of the size in total of items that you can hold in the backpack. Some people call it weight, you can call it whatever you want. But that means that we can only store at most 25 kind of, units of items in our backpack. And what our goal is to fill the backpack with as much value as possible without going over its capacity. So we can see that each item has a size here and has a value. So if we're looking at item 0, it has a size of 22 and it has a value of 19. We look at item 1, we have a size of 10 and a value of 9. And so if we were to select, say, item 1, that means that we would then be left with 15 units of capacity in our backpack, and we would have a total value of 9. So again, the goal is to maximize the value without going over the capacity, but you can be at the capacity. So you could use 25 units of space in the backpack. So the question here is, how do we use a greedy algorithm to solve this problem? And actually, I need to introduce sort of the variation of this problem, which is you can select a fractional amount of any of these items. So what that means is that, let's say we want to select item 1, but we don't have enough room for the entirety of item 1. We can select half of item 1. So if we were going to select half of item 1, then what we would do is, say 0.5 times 10, that's how much weight we're going to have for half of item 1. And then 0.5 times 9, that's how much value we're going to get if we select a fractional amount of item 1. Now, you don't have to just select half. You could select 99% of it. You could select 1% of it. You could select 10% of it. Whatever you want, you can select a fractional amount of an item. So my question is, how do we use a greedy algorithm to solve this fractional backpack problem? Well, the first thing that we should consider is, can we solve this problem by just looking at one of these columns here? So just the value or just the size. Can I select items that just have the largest value? Can I select items that have the smallest size? What is kind of the greedy approach? So let's just see what happens if we try to select items that have the smallest size first and see if that actually gives us an optimal solution. So at each step in our algorithm, we're going to select the remaining item that has the smallest size. That's kind of our greedy step. And so the first item that we're going to select here is going to be item 3 because it has a size of 7. So when we do that, we see that our current size is going to be 7 and our current value is going to be 6, and then we can cross this off because we've used it. Okay, the next greedy step is we are going to select the size of 9. So we select 9, that gives us a total size of 16, and then our value is now 15 because, well, 9 plus 6 is 15. Okay, and then we're going to select our next item. The next item has a size of 10. And when we select this item, we see that this is going to lead us to go over capacity to 26. So what we need to do is select a fractional amount of this item, which means instead of selecting all 10, we're going to select 90% of this, right? So we'll select 9 of 10, which means we are going to get now a capacity of 25. And then what's 90% of 9? Well, let me just use the calculator to get that. I probably should have been able to solve that in my head, but that's going to give us 8.1 value, which means we're going to have a total value of 23.1. Perfect. So there you go. We now have a total capacity of 25, a value of 23.1, and that's kind of the answer we got when we selected items that had the smallest size. That was the greedy choice that we made. So let me just kind of move this over to the side here so we remember this value, and now let's try it in the other way. Alright, so now we're going to perform the greedy algorithm, but this time choosing the largest value instead of the smallest size. So if I'm selecting the largest value, that means I'm going to select item 0. So we have a size of 22 and a value of 19. Then I'm going to be choosing between item 1 and item 2 because they have the same largest value. Since this has a smaller size, item 2, I'm going to select this one. And so that means that if I were to select the entire item, I would have a weight of 31. Obviously, I can't do that because that goes over my capacity. And so instead, I need to select 33% of this item. So that means that my capacity is going to go to 25. 33% of 9 is clearly 3. Same thing here. That means that I am going to get an additional 2 value here, and that is going to lead me to 22. So let's take this and store this down here as well. So the two answers we got were 23.1 and 22. Now what we can say right now is, okay, well, clearly the other approach, selecting the smallest size, worked better for this example, but is this actually the optimal answer? Are either of these the optimal answer to this problem? And well, the answer to that is no. There's actually a better way to solve this, still using a greedy approach, but it requires a little bit of thinking. So the purpose of me showing you those two methods there was to illustrate that in a lot of examples, you can use a greedy algorithm, but you have to make sure you're really thinking about what your greedy criteria is, how you're selecting the optimal choice at every single step. Now for this problem here, you have to remember that we can select a fractional amount of all of these items. And so really what we should do is find the items that have the best value to size ratio, select the largest fractions of those items that we can, and then continue on throughout the algorithm. So I'll show you what I mean by that, but let's just have a look here. So what I'm going to do is make another column, and I'm going to call this value over size. Now the point of this is that the items that have the large, quite simple size ratio, calculator fix at 0.857. So here we can see that the best item to select in terms of the value to size ratio is going to be item 2, and then we're going to have item 1, and then it's going to be item 0 followed by item 3. So now what our new greedy algorithm should do here, the correct greedy algorithm, is at each step in our algorithm, we should select the item that has the highest value over size ratio and take as much of that item as we possibly can. So in this case, we see that this is our best item. So we're going to take all of item 2. So I can just, I guess, write what our weight and our size is going to be over here. So that's item 2. We're going to select all of that. Then this guy is done. So what's the next one? Well, we want to select item 1. So we're going to select all of item 1, which means we're going to get now a capacity of 19, and we're going to have a value of 18. So this guy's done now. And then this is slightly better than this. So we're going to select as much of item 0 as we possibly can. So we need to select kind of 6 size of item 0. So let me do some math here. So we're going to select approximately 27% of item 0. So 27% times 19 gives us a value of 5.18, which means that we're going to have here 23, if I can do this correctly, 23.18 like that, and then we're going to have a capacity of 25. So we did actually end up with marginally more value by using this different greedy approach that I just showed you right here. Now, a lot of you might think that this is a calculation error. This is not. There is actually slightly more value in doing the method that I just showed you here. So selecting a fraction of this, specifically 27% of it. Now, in a lot of other examples, you'll see that this difference would be much larger. But the whole point of this was just to illustrate to you that you need to be very careful in what you actually use as your greedy criteria.
Okay, I think I'm getting kind of an idea about kind of how this works. Let me fix. Yes, now goes. For the car's capacity empty seats, the vehicle only drives east. It cannot turn around and drive west. You are given an integer capacity and an array trips, where trips I is equal to the number of passengers. The ith trip has none passengers. Passengers and locations pick them up, drop off from to respectively these locations are given as number of kilometers due east from the car's initial location. Return trips possible pick up and drop off all the passengers for all the given trips or false otherwise. I don't really understand this problem, to be honest. There's a car with capacity empty seats. What is capacity? Okay, so our capacity is 4. Okay. The vehicle only drives east. It cannot turn around and drive west. You're given the integer capacity and an array trips, where trips I is equal to none passengers from 2. Ah. Ow. My leg. Okay, so. Okay. Well, we can't hear because you got 3 passengers, 2 here, so that's 5, so it would be false, right? Then here we got 2, we start at 1, we pick them up at 3. It's the same, but we can hold 5 passengers, so this is true. Oh. Really, what would be a greedy approach here? Well, have to check our capacity, right? We start at 1. It's a pretty big sum from. Trying to think here. Best way that I can solve this problem. Iron trips print I. I think about doing 2 for loops, but manipulate this. What I'm confused about is how I can manipulate this array in order to. Equal to I. Sorry, it's meant to be passengers, start, end. Start 1 3. Okay. Now we can check. Well, create a. Oh my gosh, dude. Create a res array, right? Inside of the res array, we would do, well, res.append passengers start res.append minus passengers end. Let's print out res. I had to make a tuple. Let's do the location first. I feel like it seems a little more like intuitive to do that. Okay. So now we have to somehow sort them. So I think it's going to be some sort of lambda function, I think, in order to do this, but lambda function, Python. It's so hard to Let's load. Okay. I just don't understand how they. I don't get the lambdas, man. Okay. Why is it 5 first, bro? Okay, now we check. Well, if x is greater than capacity, then we return false. Otherwise, we can just return true. There we go. I think we could understand that algorithm a little easy, but it was just tough for me to use the Lambda functions and be able to kind of do this. Like, I don't know. But yeah, we'll leave it at that. I appreciate you guys watching. I will see you tomorrow.